So the first talk this afternoon is by Scemama, and he will tell us about the TREX IO format and library.
Hello, can you hear me?
Yeah, we can.
Okay, very good. So I will share my screen. Okay, so wait, sorry, there's a problem here. Yes. Okay, so first I would like to say that I'm very happy to speak to this workshop. So I will present you this TREX file format and library. So what is TREX? So TREX is a European Center of Excellence, and the objective of this Center of Excellence is to bring the quantum chemistry codes on eXascale machines. So here we focus on the part of quantum chemistry which is about high accuracy methods like quantum Monte Carlo and full CI QMC, for example. And inside the Center of Excellence, we have some quantum chemists, computer scientists, some supercomputing centers, and SMEs. So the software we develop, we support in TREX. So we have 3 QMC codes: QMC Chem, Turbo RVB, and CHAMP, and we are developing right now QMC KL, a quantum Monte Carlo kernel library. We support also the NICI code of Ali Alavi, quantum package, which is a selected CI general purpose code, and GAMCore, which is the code of Kasha Pernal for doing some SAP calculations. So the topic of my talk can be easily summarized with a question we had this morning in the chat. So Pedro asked this morning, is OpenMolCast compatible with VelocChem? So I will try to answer this question. So this talk will be about how to make more science with multiple codes with little effort. Okay, so we're going to use composition. So if we consider that a program is just like a mathematical function which takes an input and produces an output. So if the output of a program T1 so is this one of type T2. So if the type of the output is the same as the type of the input of a second program, then you can compose the program together, and then you can do P2 after P1, which will take type T1 and give out type T3. And in this way, you just produce another program, which is the composition of the 2 previous ones. So if we go back to the beginning of Unix, a long time ago, there was Douglas McIlroy who stated a few points to describe Unix philosophy. And so I put only 2 points on this slide, but there are many more. But here, the important thing is that the philosophy is make each program do one thing well. So only one thing. And so if you want to do something new, you will make another code instead of adding more features to the code you have. And then a second important point is expect the output of every program to become the input of another. So we see here a composition appearing because if the output of a program can be the input of another one, then it means that they have the same type. They can be plugged into each other. And here also, Douglas McIlroy says, avoid binary input formats. So we'll see later on why they have these motivations. But they, in Unix, they focus on text formats. So if we just take a few examples, which are probably obvious, we see here we can execute a few programs. So gitlog takes nothing in input, produces a string. Head takes a string input and produces another string, and cut takes a string input, produces another string. So here, this command takes nothing input and produces a string by composition. And we see that 45 years later, the Unix pipe is still widely used. So this is an indication that probably this way of building programs is something which will last for a long time. And when we look at the big monolithic codes we're used to have in the community, like for example Gaussian, they add more and more features, but they are completely closed. It's very hard to to use only a little module of the program, whether you use everything or you use nothing. So it's completely contrary to these principles that have a very long lifetime. So now let's look at the input and output of the programs of the TREX Center of Excellence. So quantum package can take in input XYZ coordinates, atomic orbitals, or even a wave function to compute an energy. And in output, you can get MOs, CI expansion, integrals, density matrices, standard quantum chemistry stuff. Then the code of Ali Alavi and Nisi. So this one takes 1 and 2 electron integrals in the MO basis set. And in output, you have a CI expansion or density matrices. And so you see that here, this code doesn't know anything about the geometry or the basis set, because you re-enter at the moment where you have the integrals in the MO basis. And the QMC codes, what you need to do to make a QMC calculation, you need a wave function, because you need to evaluate the wave function at the electron positions. So in the QMC code, you don't need any integrals and you don't need density matrices. You just need explicitly all the parameters of the wave function. And the code of Kasha-Pernaz needs integrals and density matrices. So you see here that we need, if we want to make some composition with these programs, it's going to be quite complicated, because each program needs something in input and something in output. So the situation when we started to work together was this one, where we had quantum package that was able to, it was interfaced with CHAMP, interfaced with QMC Chem, but not with Turbo RVB. We could produce FCI dump files that Nisi could read to make some calculations, and Nisi and quantum package were able to produce density matrices, but not in a format that was good for GAMCore. So there was a lot of work to do if we wanted to interconnect all the codes together. So now we've tried to answer this question: how can we build easily new programs by composition? So the answer is to make codes have all the same signature with the same type for input and output. So just like for Unix philosophy, where it's a string and string here we will try to have in the end our codes read the same file format and write the same file format. So there are two ways to do this: whether you modify completely the code, so that inside the code you modify the source file to change what you read and what you write, or you can do it also by composition, like this, by writing some interfaces where you write a converter from C to your input format, then you run your code input to output, and then you convert back again to the type T. So what I'm saying is really trivial, but I prefer to say everything explicitly. We have seen in the QMC codes here that these codes need a wave function, and so if you want to transfer a wave function from one code to another, a string type is too primitive. It's probably more convenient to use something more with more structure inside. So it's better to define, to put some abstraction on this type and define a common file format that everybody is going to read and write. So for file formats, so in Unix philosophy, they say you should do text files. So the motivations are portability, because text files, you can read them on any kind of machine. It can also be read as a stream, so you can transfer it through the network or with a pipe. You can read the data as a stream. You don't need to have the whole file to be able to understand what's inside. You can read the string in any language, so it doesn't put on you any constraint on how you're going to read it. And there is no conversion required. Everyone can write a code that reads a string. So it's the most general format. And so the problem with text files is usually the storage is quite large compared to binary, but we can use compression, so this is not really a problem. But the major problem for what we do is that the conversion from the ASCII text format to the binary representation, it's quite expensive. It uses some resources to convert a floating point number in text format into a binary representation. And so if you need to do this on gigabytes, then it's going to lead to very poor I/O performance. And so here we're trying to do high performance computing, so we prefer instead to use a binary representation. But then, if we don't want to go against this Unix philosophy, then we need to use this binary representation, but being a little bit careful. So here the solution we adopted is to create a domain-specific input-output library with a very permissive license. So here by using this very permissive license, we say that anybody can integrate this library in his or her code. Even commercial codes can use the library with no problem. So domain specific, why domain specific? Because we want to do one thing and do it well. So here we are going to write a library that's going to be good for storing wave functions and integrals and density matrices. But it's not going to be a very general purpose library able to store some molecular dynamics trajectories, etc. No, it's just a file format for wave functions, and period. And so we need also to have this library which portable. So we chose to write it in C with a C API, so that any language can call this library. There is no constraint into. I mean, if we had chosen C++, it would be a pain to call this library in Fortran. So we chose C. That's the simplest thing. And so we propose a single front end. So only one way to speak to the library from the source code point of view, and then multiple backends. So we have a text backend and then HDF5 backend. So HDF5 is a library and file format for storing binary files. And so here we propose also a text backend. And why? Because sometimes text is preferable to binary format. For example, if you have a Git repository, it's better to store text files because then you can understand better what's inside the file. And also, if for some reason you're not able to install HDF5 on your system, you can always deactivate the HDF5 installation of the HDF5 feature of the TREXIO library, and then the library has really zero dependencies. It's pure C code, and so you don't, by using TREXIO, you don't add dependencies to your code. It's just a bunch of C files and that you need to be able to compile. Okay. And so now, what kind of data are we going to store? So here we have been thinking about this problem of data for a few months, and so we decided that no external knowledge is needed to compute the wave function. So by this, I mean that psi is just a mathematical function. So if you give a form which is general enough, you just need to read a few numbers in a file, and then you're able to evaluate the function at the given positions R1 to Rn. So here I wrote all the needed numbers are stored in the file. So you don't need an external database, or you don't need to do some auxiliary integral computations. For example, normalization parameters of the atomic orbitals. Here we write them explicitly in the file because some codes might not be able to compute them for some reason. So, sorry, I'm not really in full screen. I'll try to switch. Yes, better, I guess. Okay, so an important thing is disambiguation. So I took an example here. If I say I use the basis set CCPVDZ, everybody understand what it is, but it's not enough information to be able to know really what this means. Because here I went to the basis set exchange website, and I clicked here optimize general contractions, and here I didn't click it, and I got two different files. So it's two basis sets that will give the same full CI energy, but with different representations, such that the molecular orbitals that you will obtain with this one will not be the same. You will not have the same molecular orbital coefficients with this basis set as with this one. But of course, once you evaluate the molecular orbitals at a given point, you will get the same value. But the representation is different. And so if inside the file we had written CCPV, DZ, and given MO coefficients, you wouldn't probably be able to compute the correct value, because you wouldn't know if the coefficients are expressed on this basis or this one. So that's why we chose to write all the numbers in a stupid way. We write everything, and then we read and we evaluate without asking any question. So other sources of ambiguity is all the conventions taken by the different codes. So especially for the atomic orbitals. So the ordering is not always very clear. So for example, in games, the ordering is, there is no mechanical way to know they're not computable. The ordering of the atomic orbitals in games is chosen by some user at some time. So what we decided is we chose an order in the file, and we documented what this order is. And so in Cartesian coordinates, we chose the alphabetical order, like x, 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 y, x, z, y, 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 z, 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 for example. And in spherical coordinates, so I don't remember which one we chose, but we chose one of those two. Then there are questions like, are the atomic orbitals assumed normalized or not? Should dxy have the same normalization coefficient as dz squared? So you see here, if you evaluate the overlap integral of xy with a Gaussian, and also the overlap, the self-overlap of z squared with a Gaussian, you will not get the same number. But so some codes decide that the normalization is this one, and some other codes decide that the normalization of all the d function is dz squared, the normalization of dz squared. So it depends. And when you don't know the code, you don't know the convention. And what we want is that when you read the file, you don't need to know what code has produced the file. So here we put inside the file the possibility to store the normalization coefficients, such that you just read them and you're done. So about the data stored with TREXIO. So we use a hierarchical data layout. So we store first groups, which are like directories. And inside each group, we store multiple values. So this is what we're able to store now. So data about electrons, nuclei. So this is basically the geometry, charge, etc. The basis set. And then when you expand it in px, py, pz, etc., you go to the atomic orbitals and the MOs. We can also store 1 and 2 electron integrals in AO MO basis. Information about the determinant, the CI expansion. We also just introduced some information for periodic boundary conditions and reduced density matrices. So now if we take one of those groups, so I took the nucleus group here. So we have here different variables, and so each variable is really whether a scalar or an array, where we put the dimensions here. And that's it. And so when you try to read an array, you just get the array that has been written by the user. So the names, of all the functions are you can find them once you know the groups and the variables. You can find the name of the function that you need. So it will be always TREXIO. Then you use read, write, or has. Then you have or not this safe attribute. Then you put the name of the group, and here the data you want to fetch, and then you can put 32 or 64. So this 3264 is because we have two variants. Sometimes you want to get 64-bit integers. Sometimes you want to get 32-bit integers. So here you specify the type of the data that you pass to the function. Safe is because we also have a safe API where you add an extra parameter that will avoid to have some memory overflow. And all the functions return a return code so that you can do the error handling. So the reason is that some users might want to try a function, and then if it fails, they do something. And some other users may want that when there is an error, then the program crashes. So we leave this responsibility to the user of the library. So that's why all the functions we have return code. So here is just a simple example of two function calls in C. So here you just define an array, the exit code, then you call the function. So you build it using these rules. TREXIO read nucleus charge. Here you always in first argument the file that you had opened previously, and then you put the charge array value here. And in using the safe API, here you have this max size, and inside this function, the library is going to give you at most max size elements to avoid to have a segmentation fault. So as I said, this library is usable in C, C++, Fortran, and Python. So we wrote a binding in Fortran and a binding in Python. So we are working now in a binding in Bash, so that you can just execute Bash commands to read-write your files, and also for the OCaml language. So this library has it's very mechanical. It's automatically generated, and it's generated from very simple files written in org mode syntax. So org mode is a markdown language very common with Emacs, but it's a text file, so you can use it also with other text editors. And so here I have an example where I have here the Emacs open with the org mode file. And so here you see you have a nucleus section, where here you have a little table where I put the data inside, and there is a little call, a little function called. This calls a script. This script takes this table and produces a little piece of JSON like this, and then this JSON is analyzed by script, and the library is produced from this. So basically, if you want to extend the library, you just put a new section somewhere, or you add some attributes to existing tables. You call this function, and then you rebuild the library, and then it's you get your new functions, and everything is consistent. And so the nice thing with this way of programming is that you write the documentation and the code at the same place, so you're almost sure that the documentation is consistent with the code. So here are a few examples. So first example in Fortran. So you see it's not very complicated. You need to use TREXIO. So here we don't give to the users a precompiled module file, because if you build a module file with Intel Fortran and then you use G-Fortran, you will have a conflict. So here what we tell the users is take the .f90 that we have produced and put it inside your code. And in this way, we are sure that you will not need to recompile TREXIO with the same compiler as the one you want for your code. So here you use TREXIO, and then first you open the file in write mode. You create an array. You write. First, you need to write the size, the number of nuclei here, because the charge array is dimensioned by the number of nuclei. So if I go back here, you see that charge is an array of dimension nucleus num. So here the library knows that it should be 3 in this case. So here I first write 3, and then when I write this array, so I'm not using the safe version of the function here. So the library is going to read the 3 elements of the charge array and write it in the file. But if I had made something wrong, if charge was too small, then I would go out of memory. So that's why you have this safe API also. And then if you want to read it back again, then you open the file, you read, you can read the dimension. So then you can, well, it's not needed here just to read the charge array, but it's written here. And then you can read again the array, and that's it. So here is an example of the Python interface. So basically it's the same. You import TREXIO, you open the file, and then you have the same names for the function calls. So here there is no return code because the errors are handled with exceptions, which is more the way to do for the Python users. And here when you read something, it goes on the left of the equal sign. That's the only difference from the C and Fortran API. And that's the C version, which is also very similar. So I put here just to show you here that it's always good to check that the return code is successful. So that's it. In the Fortran example, I didn't do it just because my screen is too small. Otherwise, you have too much error messages, too error checking. But it's always important to check that every time you call a function, you need to check the error code, because otherwise something might go wrong later on, and then it's hard to debug. Okay, so we also work on another Git repository, which is TREXIO tools. So it's a little repository of tools to manipulate TREXIO files. So we have, for the moment, just a few tools, like one to convert from Cartesian to spherical atomic orbitals, because sometimes we have codes that are able to compute only in spherical or only in Cartesian. So it's convenient to have a tool that can convert from one to another. We also have some tools that compute the overlap matrix in the AO basis or in the MO basis numerically, and then we can, so for the AO overlap matrix, we can compute we can compare the computed numerically computed overlap matrix with the one that has been stored in the file, and if they match, then it means that the basis set was written properly. All the normalization conventions are okay and everything is fine. And if they don't match, then it means that something is wrong. And well, if you're in a situation where you have a code that for some reason you cannot write to disk the integrals, then you can always check that the MOs are orthonormal. So then we compute here on a 3D grid, we evaluate the MOs and compute the numerical values of the MOs on this grid. Then we do the numerical integration and we check that it's the identity matrix. So if we have this, then it means that the file is all consistent up to the MOs. Also in this repository, we have converters for games Gaussian, PyFCF. So this is from the output of those three codes. And then we can also use FCIDEM to store the integrals in TREXIO. And so we plan to build many other tools. So I put a few ideas here, something like a tool that can deconstruct the basis set, reorder the atoms, because when you reorder the atoms, then you need to reorder also the MO coefficients. So there's quite a lot of little things to do. And all these little things are probably done by many people in the world. So it's probably easier if we can put everything centralized somewhere and a tool that anybody can use. We can also imagine to compute AOs and MOs on a grid, convert from one backend to another one, do this CSF to determinant conversion, compute the energy using integrals and density matrices that are in the file. It's stupid, but sometimes you just want you have your file, you want to know the energy which is inside, you can recompute it just to check that it's what you want. So we can do lots of many little tools, and all the contributions are welcome. So that's the current situation today. So for TREXIO, so now it's interfaced with all our TREX codes. And so we have contacted a few people from other codes. so that the TREXIO will be well integrated inside. So it's so for Molcas, it's Roberto Di Remigio who is involved in putting TREXIO with Molcas properly. And so what new science can we do? Now we have TREXIO. So now we can make quantum package communicate with CAMCore through TREXIO. So we can do SAPT with CPC density matrices. We can have also quantum package communicate with CHAMP in a more general way, because at the beginning there was only an interface, but now we can communicate with CHAMP, but we can also communicate with Turbo RVB. So this TREXIO has been used to check the PySCF to Turbo RVB interface, because now we can do PySCF to TREXIO and TREXIO to quantum package, check that the energy is the same between quantum package and PySCF with all the digits. So this means that the file is correct. And as we know that the TREXIO interface to Turbo RVB is correct, then it means that the conversion is fine. So now we also can compare CPC extrapolated energies with full CI/QMC, because we are sure we use the same set of integrals. Everything is the same because we use the same files. And then we can imagine some complicated things like quantum package to TREXIO to NICI we do full CI/QMC calculation, we go back to TREXIO, and then we give this to QMC to do a QMC with a full CI/QMC wave function. So now we can do by composition lots and lots of things. So it's quite nice. So now if I go back to the initial question, which was, is Open Molcas compatible with VeloScem? So the answer is almost, because you have the library to do this. So if you use the TREXIO library in Molcas, so then with VeloScem, we also have this TREXIO interface in Python. So TREXIO, you put TREXIO in the middle, and then they can exchange data quite easily. So I will finish by this quotation by some anonymous person, probably me. So it's that TREXIO will become the JPEG of quantum chemistry. That's what we hope. So I put here the different links. And that's it. Thanks for your attention.
Thanks, Anthony. We have one question from the Zoom chat from Pedro, who asks if TREX.io supports parallel HDF file.
So for the moment, we use just simple calls because this is it's a format more for transport, for transporting a wave function from one code to another one. And parallel HDF5 will be more something where you need really high performance I/O for if you're doing some calculation I/O bound. But also another thing why we didn't want to do it is because if we try to support parallel HDF5, then we will depend on MPI. So it complicates a lot the API, because then if we support parallel HDF5, we need to pass the MPI rank, we need to pass different things to the functions that are relevant only for the parallel case. But what we do is we support that it's possible that multiple threads or multiple MPI processes read the same file. But then for writing, we have a single writer, just to be sure that you don't have inconsistencies.
Yeah, thanks. One question from the audience. Speak up.
Regarding the API, there were two things standing out. First, do you really have only static fixed buffers, or can you somehow query the size of the data set you will be using, or can you pass just an?
Okay, so it depends. So if the data is small, usually you pass it in one shot. Like if it's a matrix, it's always passed in a single call. But for all the integrals and the density matrices and the 4-index quantities, or even n-index quantities, because we can also do it for 6-index, 8-index, whatever, then we have a buffered API. So it depends on the data. But for the same data, you don't have the choice of doing one way or the other. It really depends on the data.
Can I ask?
Yeah.
Yeah, and one follow-up question is regarding, for example, the Python and Fortran API, where the arrays, vectors, matrices, whatever, already have their shape and corresponding length. Do you have kind of shorter APIs that just avoid the redundant setting of the size of the array?
So that's the unsafe API. So sorry, I'm going to just to go back. Yeah, but here you see read nucleus charge, you just pass F and charge. You don't pass the size again.
But you have, in order to do that, you have to know when you write it. For example, where you have to first write the number of nuclei which are already contained in the array size. Anyway.
Yes, because you could imagine that you have an array that is larger than because you imagine some people who write old Fortran 77, they will have very large arrays and they will use only the beginning of the arrays because they don't know at compile time the size. So there are situations where the array will be too large. So you need to give this information to the library. But I understand your question, but the thing is that if we put more and more intelligence in the API, then first it will require the users to be more and more intelligent. This is not probably what we want, because then the audience will become more and more restricted. So simple is the best. So we prefer to have something which is extremely simple. And so yeah, maybe you need to do it in 2 function calls instead of 1, but merging calls, then you have a function that does 2 things at the same time, then it starts to be hard to handle in the long term.
Thank you.
Okay, thanks, Anthony, for the interesting talk. And I think we will move on to the next speaker, who's also online, Michał Hapka. Yeah, sorry. Thanks.